Today we'll be discussing another aspect of the statistical analysis of data, and that's how to fit data. In other words, when you have two random variables, we'll call them x and y, how do you understand the relationship between x and y? The approach to data fitting that we're discussing today is known as linear regression, and it's a technique for finding the functional relationship between a variable y, which you believe to be a function of a variable x, where x and y are both random variables, as we've described in class. In particular, this technique is applicable when you have a functional relationship between x and y that appears to be a straight line. So if you have data scattered as such, and you can fit a straight line to those data, then linear regression is an applicable approach. The question then becomes, how do we determine the equation of a line that best fits the measured data? Let's say we have these data points y sub I to a set of fit values. In other words, for each data point y sub I, we have a fit value x that is related to y sub I by a line. So we'll have two constants, the slope, which we'll call a1, which is multiplied by an x value, and the intercept, which we'll call a0. These x values, x sub I, then are either experimental parameters, measured time points, but they represent data too. X sub I is also another random variable, just like y sub I. So to determine whether these fit values represent the data yi well, we can determine an error at each fit value. That error is referred to as a residual. So at each fit value, we have the residual e sub I, which is going to be equal to the actual measured variable value minus the fit value, which is what we get by fitting our x data to our equation of our line. All right? So if this line equation perfectly explains the data yi, the residual ei is going to be 0 at every point yi. The difference between this value, the equation of the line, and the data value y sub I is going to represent how far our equation is from perfectly representing the y data. The question then of finding the best values for the line coefficients, slope a1 and intercept a0, then becomes the question of minimizing the residual values at each point. To accomplish this minimization, what we're going to do is we're going to express this error ei as a function of the two parameters, slope and intercept, and we are going to minimize the value of ei with respect to those two parameters. All right, so we'll treat a1 and a0 as variables, and we will minimize ei with respect to those variables. Remember, we're going to have one value of a1 and one value of a0 for every value of x and y. So what do we actually want to minimize here? Well, you could take all of the residuals, add them up, and try to minimize the sum of the residuals. But the problem with that is that if some of the residuals are negative and some are positive, the negative values can cancel the positive values out, and you can wind up with a sum of residuals that's close to 0, even if each individual residual is a relatively large number. So what we do instead is we minimize the sum of the squares of the residuals, such that both negative and positive values go to a positive square, and then we minimize the sum of the squares. So we're going to define this S sub r, which is the sum of the squares of the residuals, which if we again take the equation for the residual is simply going to be the sum over all the y values minus slope times the x values minus intercept. This whole thing squared. So to minimize this, we'll simply take the partial derivatives with respect to the two values that we're interested in finding, and we're going to set both of those partial derivatives to 0. So we'll take the partial derivative of S sub r with respect to a0. We set that equal to 0, and then we take the partial derivative with respect to a1. And we also set that partial derivative equal to 0. So we now have two equations. Equation 1. Equation 2, and two variables, a0 and a1. So we can simply solve these two equations and we'll get a value for each of the variables. Expanding these two equations, we get the sum over all y minus the sum over a0 minus the sum over a1x equals 0. And then from the second equation we get sum over x times y minus sum over a0x minus sum over a1x squared is equal to 0. Now we use the fact that this summation is simply a0 added to itself n times to reduce this term to n times a0, where n is the number of data points that we're summing over. Rearranging these equations, we then get the following. This is from equation 1 and from equation 2. We now simply combine these equations and we will solve for a1 and we get the following. Now remember, you have all of the data values. You have all your x's, you have all your y's, and you know the number of points, n, right? So given your data values and given the value of n, you can compute the value of a1, which is the slope of your line, precisely. a0 is then simply where y bar and x bar are the means of the values measured for x and y. So given all this, we now have an equation that best fits our data, giving our value yi equal to a1 xi plus a0. Slope-intercept form. The next question we'll look at is how good is this equation? In other words, how well do the two slopes that we've calculated, or our two values that we've calculated, our slope and our intercept, how well do these two values actually represent the values of data yi when we feed the equation the values of data xi? To think about this, let's go back to the sum of the squares of the residuals. We call this S sub r. On the basis of this value SR, the sum of the squares of the residuals, it's possible to define something called the standard error of the estimate. And this is a standard deviation that basically describes the standard deviation of y with respect to x, and it is simply defined as the square root of this value SR over n minus 2. Based on this value, then, it is possible to assign a standard deviation to each of the coefficients. Now treating the coefficients as random variables. The standard deviation for variable a1 is simply going to be this standard error of the estimate squared over the following summation, basically the residuals of the means of the x's. So each value xi minus the mean value of x, that whole thing squared. And based on that, you can then get a standard deviation for the intercept. This will simply be equal to the standard deviation for the slope times the square root of 1 over n times the sum over all x squareds. Another way to think about how good our linear fit is to think about how well an equation of a line describes the relationship between the two sets of data. All right, so we presumably have y as a function of x and a bunch of points scattered along the xy axis. Now we can think about two ways of representing the statistics of these data. We can think about the mean of the data in terms of y, right? This is going to be the value y bar that we've previously discussed. We can also think about the best linear fit of these data. And the question we're going to ask now is what better explains the scatter of the data? Is it simply the mean, y bar, or is it the linear fit that we've developed, which, if you recall, is a1 x plus a naught? If you think about this situation relative to this situation, where the data are scattered around the mean regardless of x, clearly over here, the line does a better job of describing the data than the mean of y does. But over here, if we were to draw a line that best fit the data, it would be the same line that describes the value y bar. So the linear fit of y to x does not do a better job of explaining the scatter of the data than simply taking the mean does. All right, so what we need to do now is develop a way of measuring whether y actually depends on x. And the tool that we're going to look at is this value s sub t, which is simply the sum of the squares of the residuals around the mean of y. Clearly, this value is going to go to 0 if the mean explains the data y precisely. In other words, if every y value is equal to the mean, s sub t goes to 0. We also have s sub r, which you'll remember is equal to the sum of the squares of the residuals for our linear fit. And this value is going to go to 0 if our linear fit is a perfect description. So on the basis of these two values, we're going to define what we call the coefficient of determination. And this coefficient is represented by the symbol r squared, and it is simply equal to the sum of the squares of the residual about the mean minus the sum of the squares of the residual about the linear fit, all over the sum of the squares of the residual about the mean. Okay, so our coefficient of determination is going to go to 0 as st approaches SR. In other words, if the mean describes the spread of the data just as well as the linear fit describes the spread of the data, then the linear fit is not a very good explanation of the data. In other words, y is not dependent on x in a linear fashion. On the other hand, r squared is going to go to 1 as SR goes to 0. In other words, if our linear fit is a perfect explanation of the data, then we're going to have a coefficient of determination equal to 1. So the closer the coefficient of determination is to 1, the better an explanation our linear fit is for the scatter observed in the data. Now, so far the linear regression we've talked about can only be used to fit linear equations, that is, equations of line and slope-intercept form to data. What happens, however, if we have data that are not related to one another by a linear fit? Well, in this case, in many cases, we can linearize the relationship between the data. For instance, let's think of what happens when we have a relationship between the data that looks like this. Where there's apparently an exponential relationship between y and x. So we can represent generally y is equal to some parameter alpha times e to the beta x. Well, we can simply turn this equation into a linear equation by taking the natural log of both sides. Right? So ln y is equal to ln alpha plus beta x. So now we have a linear relationship between x and the natural log of y. So if we plot axes with x and the natural log of y, we have a linear relationship. And the slope of this relationship is going to be beta. The intercept of this relationship will be the ln of alpha. So simply by using the data that we have, our y data and our x data, taking the natural log of each y data point, we can determine a relationship between x and y using a linear regression after we transform the equation relating the two variables by taking the natural logs of both sides. As another example, we can do something similar if we have a power law relating x and y. So if y is equal to alpha times x to the beta, then you linearize again by taking the natural log of each side. And now if you plot the natural log of x against the natural log of y, you have a straight line, the slope of which is beta, and the intercept for which is the natural log of alpha.